Okay, welcome. We're going to continue on here. Hopefully, you had a good break. And we are on chapter two. I did send out an announcement because of the holiday and stuff like that. I did post a recorded chapter three lecture. It's not too long of a lecture. So make sure you watch that. You're responsible for obviously what's in there. And that will hopefully kind of get us back on pace or keep us sort of on pace with what we need to be. So we're going to obviously continue on here with chapter two for a bit. And that'll probably be it for today, I imagine. All right. All right. So last time we talked about obviously units, and then we got into really scientific notation last time. And remember that when we do write something in scientific notation, it is this sort of format, n times 10 to the n. Remember that the first number here is a number usually between 1 and 10. 1's okay, can't be less than 1. And usually, again, as we talked about, you don't usually use 10, so you just be a little bit below 10, 9 point something. Times 10 to the little n there, which as we talked about is either a positive or negative number, depending on really which way you need to move the decimal place to get to a number between 1 and 10. Um, Remember that when we do see a number written in scientific notation, so if we had 1, 2, 4, 5, and we want to put it into proper scientific notation, we would move the decimal place 1, 2, and 3 places to the left. That's going to give us a number of 1.245 times 10 to the 3. It's a large number, so it's a positive exponent there, and we did have to move it 3 places. When we do write a number in scientific notation, once it's written in scientific notation, all of these numbers that come in front are significant figures. So these are all sig figs. So this number here would have 4 significant figures the way that it is written. We always, if it's written in scientific notation, look before the times 10 part. That tells us how many significant figures there is. As we talked about last time, again, a very common mistake sometimes people will make if they're asked a question like how many significant figures are there in that number, they'll oftentimes perhaps convert it into a decimal, then try to figure out the significant figures. Remember that if it's written in scientific notation, it just straight up tells you the number of significant figures. As we also talked about, we'll talk about maybe a little bit more today as well. Sometimes scientific notation is the only way to give the answer to the proper number of significant figures, as you can again control how many significant figures your number has. Again, here, if I just wanted 3 significant figures, I could write 1.25 times 10 to the 3. Now I would have 3 significant figures. So you could kind of play with scientific notation in a sense that you can give as many number of significant figures as you want. And again, sometimes you can't really give an answer in sort of decimal form to the proper number of significant figures because there's just no way to do it and still have the correct number that you're looking for. Probably more importantly, what we talked about was again using your exponent button when you do punch it into your calculator. So again, on your guys is there, you have that EE button, and that is your exponent button. That should always be the button that you use when you put a number in scientific notation. You also have I call it a negative sign, but it changes the sign type button. That's what you should use. You should never use the subtract button. So again, if we were going to put, say, this guy in scientific notation, you would on your calculator hit 1.25. You would hit that EE button. When you hit that EE button, that represents the times 10 part of the number. So you do not need to hit the multiplication button or anything like that. In this case, it's a positive exponent, so you just hit 3. Now, again, if you don't hit equals on your calculator or anything like that, it most likely will pop it up looking something like that. Obviously, in this case, if you hit equals, it may turn it into just a regular decimal number, depending on how you have your calculator set as to sort of non-scientific notation. Um, Again, if we had a negative exponent, basically same idea. Thank you. Uh, -4. You would go 1.25. Again, you would hit your exponent button. You would hit your negative button and 4. And again, probably will display something like this on your calculator again before you hit equals or anything like that. It'll probably look something like that. Also important, as we talked about on your calculator or really any calculator, is when you do get an answer, if it does give it to you in scientific notation, again, you may have a bunch of numbers and then like a couple of numbers up on top. You want to make sure you don't forget that numbers on top. That's the times 10 part. So that would be times 10 to the 42. And again, sometimes people just get the front part of the number on their calculator and forget the sort of exponent part when they're given the answer. Any questions on any of that there? All right, then let us continue on. The next thing we're going to talk about is, there it is, uncertainty in measurements. And when we take a measurement, that's a quantitative value, and that is based up of numbers and measurements that are taken. And depending on what device you use, there's always some degree of uncertainty associated with it. So it doesn't really matter, what device you're using. There will always be uncertainty associated with a measurement. There will always be some type of estimation that you have to make. And we're going to talk about how to properly take a measurement here. So for example, let's just say we had a ruler. And we'll go with our friend centimeters here. And let's say that we had some type of arrow we wanted to measure. We'll put it right about there. Now, it doesn't really matter what type of equipment that you're using, be it a ruler, a piece of glassware, whatever like that, whatever it may be. You always want to really look at the markings that are on the piece of equipment. And you always want to look at the markings to know really how far you should take the reading to, how far you could take your measurement to. So there's usually two types of markings when you look at a scale on a piece of equipment. There's usually what are sometimes referred to as the large markings. And there are the small markings. Now, usually the larger markings on a piece of equipment, such as this, will actually have numbers associated with it. So in this particular case, our large markings, the difference between the two large markings that have numbers is 1 centimeter. So in this case, each of the large markings would represent 1 centimeter in this case. Now, the small markings are the markings that are really between those two numbers there, the markings between the two large markings. And it's important when you count the small markings that you do count it correctly. So typically when we're counting the small markings between the larger markings, we always start after the last large marking. So here we would start counting here. This would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and we would stop at the next large marking. So when you're counting those smaller markings, you start after the last large marking and you go to the next large marking, and that's where you stop. So in this case, we have 10 small markings in this case. And that means each of the small markings represents how much? If there are 10 of them and the big markings are 1, each one represents 0.1 centimeters. If you're not sure, you could take this guy and divide it by 10, and you get 0.1. That would mean this is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then obviously the big marking there to 2. Any questions on that there? So when we take a reading, no matter what piece of equipment that we use, there should really always be numbers that pretty much everybody should agree upon, no matter who's taking a look at it. I look at it, you look at it, everybody should agree. So here, if we take a look, we could definitely probably all agree that our arrow here is at least 1.4. And we would record 1.4 in this case. And these numbers are sometimes referred to as all the certain numbers. So these again are all the numbers that, pretty much no matter who takes a peek at it, everybody should really agree upon. Now we could clearly see when we take a look at our arrow that it's really not exactly at 1.4. It's really not exactly at 1.5. And this is where the uncertainty in this measurement comes from. This is where really an estimation sort of has to happen. So in this case, I may look at it and go, well, I feel like it might be halfway between those two markings. And I may record a 5, along with obviously the units. And this is what is sometimes referred to as the first uncertain number. And it's uncertain because somebody else may look at it and go, well, I don't think it's exactly half. Maybe it's a little less, so maybe I want to record a 4. Or maybe some people may feel like maybe it's a little further than a half. Maybe they want to record like a 6 or a 7. So again, there's some estimation that occurs here. And the proper reading here would be 1.45 centimeters. When you take a measurement, you should always record all the certain numbers plus the first uncertain number. So whenever you take a measurement, these are always the things that you should record. Should always record these guys when you take a proper measurement. The reason why that is really, really important is because when you do that, these guys are what are commonly referred to as significant figures. That would mean that my measurement right here would have how many significant figures? This number, it would have 3. All these would be significant. This would have 3 significant figures. So it's really important when you take a measurement that you do take it to the proper number of digits, and it does change based on the equipment that you're using, the markings that you're using. Sometimes you may even be using the same piece of equipment and say maybe somebody next to you is, but maybe it was made by 2 different people and there's different markings on it. So it can be different in a sense. Just you always should look at the proper sort of reading. Now, this is how we would record this as 1.45 centimeters. Now, if we take the smallest reading or the smallest markings and we divide it by 2, this will sometimes give us the uncertainty in the measurement, or sometimes the tolerance is referred to. And a lot of times here at this school, they do want you to include it in your measurements. So if we take the smallest markings here and divide it by 2, that's going to give us plus or minus 0.05 centimeters. And that's really the uncertainty in this particular measurement. And the proper way at this school that they would like you to record measurements in the lab and such is you would record 1.45 centimeters plus or minus 0.05 centimeters, right? Any questions on that? Obviously, the uncertainty lies in the last digit. You're basically saying, I think in this case it's 1.45, but hey, it might be like 1.46, might be like 1.44. The uncertainty lies in that last digit. Question? You do. They do want you to do that here at this school. I would say other places, not so much. Yeah, so in the laboratory, and we'll talk about it, in the laboratory, they would like you usually to get in the habit in this class, and as you continue on, obviously in the other classes, to record the uncertainty with your measurements there. So they would want you to record it. And what we'll do in our labs here, just to obviously get you used to doing it, is that would be the way that you record it. Everywhere else in the world, probably they just record that and call it a day. But here, they would like you to include the uncertainties. So you should get in the habit of kind of doing that. Not with calculations, but just with measurements that you take, for example, in the lab or something like that.
Is it whatever you
No, it doesn't matter. It doesn't matter. So, for example, on this scale, right, on this ruler, if we had the rest of the ruler, right, the next large marking would be 3. So the difference between here is still going to be 1 centimeter, and there will still be 10 smaller markings. So the uncertainty is from the smaller markings. So you always divide the smaller markings by 2. Always by 2, yeah. Now, it can also help you know how far to take a reading, and we'll talk about that in just a second, but we'll come back to that here. Other questions? Now, let's just say we had a graduated cylinder here, and 20, we'll do milliliters here, and we'll put some liquid in there. And by the way, when we put liquid into a glass container, we typically will see dramatically drawn here a curvature of the liquid here. And the reason for the curvature of the liquid is the attractive forces between the liquid and the glass are stronger than the attractive forces between the liquid and itself. So through capillary action, what happens is where it's in contact with the glass, it starts to rise up the sides of the wall. This is known as a meniscus. Very badly spelled there. There we go. And when we read a liquid, we always want to read from the bottom of the meniscus. In most cases, especially if you have a U meniscus, you always want to read from the bottom, because without that interaction with the container, the true volume that's in that container is what's in the middle, where it's not touching the wall, so it's not rising. That's where the true volume is. So in most cases, you do want to read from the bottom of the meniscus when you're taking a volume reading. Some cases it's easier to see that kind of curvature of the liquid. Other cases a little bit harder. If you have a bigger beaker with a bigger diameter, it's very hard to kind of pick up the meniscus, which is why beakers are very terrible things to measure out volume. Something like graduated cylinder has a smaller sort of diameter of opening there. It's a little bit easier to sort of pick up the meniscus. I would say 99.999 times out of 100, your meniscus, when you see it, will look like a U. It actually could go the other way. You probably don't see it too much anymore, because one of the most common things that can do that is mercury could actually go this way. And that's because the attractive forces between mercury in itself is actually stronger than the glass and mercury, and actually comes in on itself. And in this case, you would actually read from the top of the meniscus. But again, I would say probably almost 100% of the time, the meniscus you're going to see is going to be more of a U-shaped rather than the inverted one. But mercury is one of those ones where it kind of flips the other way, and you read from the top. So again, this is most likely what you're going to see. So when we look at this graduated cylinder, once again, we want to sort of figure out our markings and what they represent. So our large markings here, which have actual numbers, that is 10, that is 20, which means our large markings in this case represents 10 milliliters. That is the difference between the large markings. Once again, if we count our small markings, making sure that we do count correctly starting after that large marking. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, stopping at the next large marking. We have 10 small markings. That means in this case, each small marking represents how much? 10 divided by 10 is 1 milliliter. Yeah, so each of these small markings represents 1 milliliter. If you divide it by 10, that would then be 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So once again here we have sort of a U-shaped meniscus, and if we read from the bottom of the meniscus here, we can definitely see that it is at least 15. So in this case, we would want to record 15. These again are going to be our certain numbers. Once again, we do have some type of estimation that needs to be happening here. And maybe in this case, you feel like maybe it's more than half. So maybe you record 15.6, and again, our units with it. This would be our first uncertain number. That would mean in this case, this number would have how many significant figures? Would have 3 significant figures. The uncertain number would be, or the estimated number would be the 6 in this case. Once again here, if we take the smallest marking and divide it by 2, that is going to give us plus or minus 0.5 milliliters, which would give us our proper way of recording that here at this school as 15.6 milliliters, plus or minus 0.5 milliliters in this case. Any questions on that there? So it is really important to make sure that you do look at your piece of equipment, that you do look at the scale and you understand what it is. Because again, you could have something come back to another graduated cylinder. And maybe we start with 10 and 20. And we'll just kind of pop it right about there. All right, in this case, our large markings represents how much? Large markings represent? Our large markings in this case is still 10 milliliters, right? The difference between these. So those are our large markings. That still represents 10 milliliters. In this particular case, though, we actually have, in terms of our small markings, 1, 2, 3, 4, and only 5 markings in this case. So our small markings are only 5. That means that each small marking in this case represents how much? 2 milliliters, right? 10 divided by 5, right, is 2 milliliters. That would mean that this marking is 12, 14, 16, and 18. So even though this graduated cylinder has the same large markings, it does not have the same number of small markings, which means the scale is different than the one we looked at a second ago. Now, when we look at this and we want to take a measurement, once again, we want to look at it and we see that our meniscus is right about there, and that is 14. That is 16. What becomes between 14 and 16? 15. So in this particular case, 15 milliliters is actually the best we could do on this particular scale. The reason for that is I have no idea between 14 and 16 where like 14 ends and 15 starts. There's just like too many kind of dashes to try to figure that out. That's different than if the 2 large markings like the last one was just like 1. If it's just like, oh, a difference of 1, like halfway is half the way there, right? But obviously here, don't know where 14 ends, don't know where 15 starts. There's no way to go any more than 15. That would mean in this particular case, how many significant figures does it have? This number has 2 significant figures, right? So this has 2 significant figures. This would be my certain number. This would be my uncertain number, right? And if I do this and divide it by 2, right, it would tell me that really plus or minus 1 milliliter is the best I could do on that measurement. And we would record something like 15 milliliters plus or minus 1 milliliter. Any questions on that? Now, in most cases, you can go to one more place to the right of the smallest marking. Not in all cases. Obviously, here we can't, right? Here we could only go to really the kind of the big marking there. It's 1 because that is as far as you can take the measurement to, which is 1 milliliter is where the uncertainty lies. The first whole number is the best you can do on the scale, basically. And what this tells you, by the way, is if you are not sure, for example, you look at a scale, right? And on a piece of equipment, you're like, I'm not sure really how far I should take the reading, but you are sure of what the large markings represent, what the small markings represent. If you are 100% sure of what each of the small markings represent, all you have to do is divide it by 2 to get your uncertainty, and it will basically tell you how far you should take your reading to. That is a whole number. That is where we should take our reading to. If we look back on this one, that is the first decimal place. That is exactly where we should take our reading to. And if you come back to this one, that is 2 decimal places. That's exactly where we could take our reading to. So if you are very confident in just looking at a scale and being able to figure out what each small marking represents, if you want to know for sure how far you should take that reading to, all you have to do is take the smallest marking divided by 2, and it'll tell you how far you should take the reading to. If you do that and it goes to 3 decimal places, you should take the reading to 3 decimal places. If you do it and it goes to 2, you should take the reading to 2. If you divide it by 2 and it goes to 1 whole number, you should take it to a whole number. So the plus or minus can be very helpful, especially again if you are able to very confidently know, okay, I know what the small markings represent, divided by 2, that tells you exactly how far you should take your reading to. Any questions on that there? Now, very common error, we'll just go and take a look at this, which is, we'll use the same sort of ruler we used before. Drawing not so great, but we'll go with it. They didn't have quality control at the factory that day. All right. We'll just go right here to, so let's just say we had a error right at the marking. And in this particular case, just like we saw earlier, our large markings are 1 centimeter. We have again 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings, smaller markings between them. So we divide that 1 centimeter by 10. That, just like we saw before, is going to give us 0.1 centimeters as what our small marking represents. So this is 1.1, 1.2, 1.3, 1.4, 1.5. So if I'm going to take a measurement of that arrow, it's dead on the line. I record 1.4 centimeters, 1.40 centimeters, 1.40000 centimeters. Is there any difference in the way I record it? Does it matter if it's right on the line? It does matter, and that's why it does matter. We want to make sure that we do record it properly. So for example, if we take, say, this recording right here, this would have how many significant figures? This would have 2 significant figures. The uncertain digit is the 4. So when you take this measurement and you record it like that, you're basically saying, I think it's 1.4 centimeters, but maybe it's 1.5, or maybe it's like 1.3. And that basically is a lot of error between that range there, right? And we could clearly see from our measurement there, it's really nowhere near those other 2 numbers, but you now just introduced a lot more error that should not be there based on your scale, right? Now, if we take this guy, actually, we'll go this guy first. If we take this guy here, how many significant figures would it have? This guy in the box. It does have 3 significant figures. The uncertain digit is, in this case, the 0, right? Is our first uncertain number. And that would mean, in this case, I go 1.40 centimeters, which is basically saying I think it's 1.40, but it could be like 1.41. It could be 1.39. That is an error of, like in that ballpark, right? And that is really realistically what we're seeing here on this scale. We're able to basically dial it down to that level. And that is why this one here is the correct way to record it. And you would record just like we did before, 1.40 centimeters plus or minus 0.05 centimeters in this case. So sometimes people will loft off the number and not record the 0. And what you're doing is you're making your measurement pretty crappy in that case. So you're making a lot more crappier than it should be. You're putting a lot more error in there than you should have based on the scale that you're using. So you want to make sure that if you're able to, like in this particular ruler, take it to the 2nd decimal place and it's right on a number, you do need to put a 0 in there to maintain the proper number of significant figures and not make your measurement worse than it should be based on the equipment that you're using. Any questions on that? Now, just like not taking off a 0 is important, adding zeros here also not so great, because in this particular case, how many significant figures would that one I just circled have? It would have 6, I think. I haven't counted, but 1, 2, 3, 4, 5, 6. All those numbers would be significant, right? And the uncertain number here would be way over here, right? The very last 0. And basically what you're telling people is you're about 5 decimal places of uncertainty there, which would be like a dot maybe on that scale, which clearly you can't do on that particular ruler. So adding zeros, extra zeros, are not good as well, because what you're doing in that case is you're telling people my measurement is a lot better than it should be based on the equipment I'm using, right? So you shouldn't make your measurement crappier, and you should make your measurement better, because the piece of equipment you're using only allows you to make it what it should be, and you want to get it to the proper number of digits. Any questions on that there? So that is, again, a really important thing to think about. People, very, very common, just, lop off numbers and stuff like that. I'm always amazed when people do things. They're always right to the nose, always perfect. I sat there at the balance and sat there for an hour and got exactly 25 on the nose. So you should make sure that you record what you see. By the way, if you have something that is digital with a digital display, typically all those numbers are significant. So you should always record all those numbers. Speaking of weighing things out, that is also a very common error that people make. The balance gives them like 52.456 grams, and they go, cool, 52 grams, looks good. Yeah, I just lost all those significant figures. Yeah. So if it's digital, you do need to record every digit that you're there and assume probably the last digit is where the uncertainty lies. Any questions? By the way, the uncertainty in the measurement is not always the last number, but it is always the last significant figure. And what I mean by that is this. Let's say I had this measurement here, 12,000 centimeters. What is the uncertain number in this case? It's actually not. It's actually, in this case, the 2, as the 2 is the last significant figure. This number, as we'll talk about in just a second, has actually only 2 significant figures, the 1 and the 2. And the 2 in this case is actually the estimated digit. I would say 99.9% of the time it's going to be probably that last number you see, but it will not always be the last number. So sometimes people always think it's always the last number that's written. It is always the last significant figure that's there. So since this guy only has 2 significant figures, the 1 and the 2 is actually the estimated digit. Any questions on that there? All right, there's our ruler and our measurement. So the importance of taking a measurement properly, as I mentioned, is, again, when you do that properly, which you should, you are basically recording the proper number of significant figures. And significant figures are really important, especially in calculations, as we'll talk about. When you do calculations, your calculation is only as good as your worst measurement. And your worst measurement probably has the least number of significant figures and so forth. And that is really where significant figures plays a big role in calculations and stuff like that, and why you want to take it to the proper number of digits. Again, if you're kind of shorting out significant figures in your measurements, your overall calculation of whatever you're going to do is going to be probably a lot worse. That brings us to a difference between 2 terms, which is accuracy and precision. Accuracy tells us how close the value that we have is to the true value. Precision tells us, though, how close a set of numbers are to each other. So usually accuracy, or being accurate, we look at how close you are to sort of the right value. Precision, a lot of times we deal with how close you are to the other numbers. And what that comes into play is a lot of times in chemistry or science, just in general, when you do experiments, you oftentimes will do it multiple times. So you'll do multiple trials of the same experiment. And what that will allow you to do is figure out, for example, is this experiment perhaps reproducible? So if you have a low precision, that means that you're able to reproduce this experiment and get the same result every time. May not mean that you get the accurate result every time, but it has to do with precision. So two very common sort of calculations that we do is we do percent error. We'll talk about later on in the semester. We use that a lot of times for accuracy. And we do something like standard deviation or percent deviation for something like precision. So common example of this is if we're throwing darts, for example, and we want to hit the bullseye in the middle is the goal, and I throw my darts the first time, and I hit here, I missed the board, whoops, hoping nobody's standing there. I hit over there. Am I very accurate? The goal here is to hit the center. Am I very accurate? Yes, no, no, right? Am I very precise? I am not. I'm all over the place, right? Including I missed the board completely, which is a little embarrassing. So like any good person throwing darts, right, we'll go double or nothing, right? So I pick up my darts, maybe some of my pride as well there. And I throw them again. And I land them, boom, boom, and boom. Am I accurate? I am not. The goal is to hit the center, right? So I did not hit the center. Am I precise? Yes, I'm precisely not accurate, right? Which means a very good point, which is you could screw up an experiment and do it the same wrong way every single time and get the same wrong answer, right? So you're very precise in the way that you're doing that experiment, which just happens to be wrong because you're not accurate, right? So you definitely do something wrong same way all the time and not get the right answer. All right, so obviously did a little better there, managed to find the board. So we'll go triple or nothing, obviously. And I'm going to make it easier, or maybe harder there. I just made the board smaller. We'll put back some of the board so it doesn't look like I'm cheating. All right, so now I take my darts and I lay them up and I throw them. And I hit boom, boom, and boom. Am I accurate? Am I precise? Did I just hustle you? Probably. I probably did. That's why you don't bet money. Not a good idea. Yeah, so that's what we're shooting for here, not to hustle anybody, but we're shooting here to be accurate, right, when we do things, and we also want to be precise. So we want to get the right answer, and we want to be able to reproduce, say, experiments and come up with the right answer every single time. Any questions on the difference there? And again, as we can see, our darts there, we're inaccurate and imprecise on the first one, all over the place. We're precise but not accurate, and then obviously there in the center, we are accurate and precise. All right, so why don't you take a moment here and think about what the blue line reading should be. These big numbers go with the big lines, so they just kind of got moved a little bit. All right, so take a moment there. The one should be the right reading here. And maybe the right reading ain't on there because things move. Things move. I'm going, I don't think the right reading's on there. Things shifted. So take an actual reading. Just ignore this part down here, apparently, since things shifted around. All right, we'll take a reading on what it looks like. I feel like there's not the right choice there. There should be none of the above answer up there would be good. All right, let's take a look at this one here. Again, things kind of shifted a little bit, I think. So we will look between our large markings, which is here, that's 2, and that is 3. So again, our large marking in this case is 1 centimeter. Small markings, we got 1 there, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, our small markings here is going to be 0.1 centimeters as we divide it by 10, and that would give us there. So looking at where it ended up, this one, which is clearly none of the choices there, this would be obviously right here, 2.5. That would be 2.6, 2.7, 2.8. It looks like it is before the arrow. So it should at least be 2.8, right? As those are our certain numbers to where it ended up. Now we have our estimation, and then obviously if we kind of zoom in this case, it does look very close to the 2.8 marking. It doesn't really look half. So remember, sometimes people think you always got to go like 5 as the last one or something like that. You don't. You can pick whatever number it looks like. In this case, I would say maybe it will go 3 centimeters, right? And in this particular case, this would have how many significant figures? It would have 3 significant figures. We know if we take our small marking and divide it by 2, that's going to give us a plus or minus 0.05 centimeters, which tells us we should go to 2 decimal places, which is what we did here. So to fill it out there, 2.83 centimeters plus or minus 0.05 centimeters. I felt like it moved a lot based on our choices there, I think. Any questions on that there? Is it right? Is it on it? Better? Yeah. Okay. I'm like, that didn't look right to me. All right. So, any questions on that reading there? So the answer would be none of those because clearly on my slide here it shifted badly. I'm assuming this one might have shifted badly as well. So why don't you just maybe read it based off of what it looks like up there, and we'll just kind of figure it out, just in case it moved as well, which it looks like it does since it's all of them are 9. And again, the big numbers are here. Okay, so let's take a look. Again, we'll just do our scale. We have big number there, big number there. So large markings on this one also going to still be 1 centimeter. We should again have 10 markings between. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That again will give us pretty much the same scale there, 0.1 centimeters by dividing that by 10. So that would be 8.1, 8.2, 8.3, 8.4, 8.5, 8.6, and 8.7. So definitely it's 8.7. These again are going to be our certain numbers. And again, at this point, if you're not sure how far you should take the reading, you could always just divide that by 2 to begin with if you're good on the small markings. And again, that's going to tell you plus or minus 0.05 centimeters. So that right there tells you 2 decimal places is where I need to take it. So again, if you're not sure, you hopefully will not stop at this point at 8.7, which is obviously only 1 decimal place. You can and should take it on this scale to 2 decimal places. And again, in this case, we look a little bit closer to half. Maybe you still feel it's a little short, so maybe 8.74 centimeters plus or minus 0.05 centimeters in this case. And once again, this number here would have 3 significant figures. Any questions on that one there? Obviously, my example here moved from what's in the book there. All right, let's take a look here. This is graduated cylinder. We have our meniscus. And again, we want to read from the bottom. So take a moment there and record what you think the proper reading here. Okay, let's take a look. So again, when you have liquid in a glass container, you're going to be looking for that meniscus. Like I said before, 99 times out of 100 there or even more, it's going to be that U-shaped meniscus. So we want to read from the bottom. We still want to look at our scaling here. So again, the big marking right there is 30. That is 40. So our large markings in this case is going to be 10 milliliters. We count our smaller markings. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So in this case, if we divide that by 10, which is the small markings, that will tell us each of the small markings in this particular scale represents 1 milliliter. That would mean that right here is 31, 32, and so forth all the way up. That would mean that right about here is 35, 36, and 37. So once again here, we are at least 36. Everybody should agree upon that. So we do want to record that. And again, if you're not sure how far you should take the reading to, but you are sure about this number here, all you have to do is divide it by 2, and that'll give you your plus or minus 0.5 milliliters. So again, that tells me I should take my reading to 1 decimal place. So I am not done reading at this point, right? I can't just put 36 or anything like that because that would be incorrect. Again, you want to kind of feel like where it's at. You may feel, again, it's in the center between the 36 and 37 lines. So we'll go zero point 0.5 milliliters plus or minus 0.5 milliliters. This would have 3 significant figures, with the 5 being our uncertain, our estimated number in this particular case. Any questions on that reading there? So again, that plus or minus, which is kind of a pain to put on measurements, and they do want you to do that here, it can also be very helpful because, again, if you're very confident on that small markings and just divided by 2, it will tell you how far you should take the actual reading to. Any questions on that there? Okay. All right. Now, sometimes we do use glassware that's a little bit different, and this is a burette. And we use a burette when we do titrations and some other sort of experiments, but very common we'll use it towards the end of the semester. The difference is on a burette is we fill from the top, and it does come out the bottom. And when we look at the scale of a burette, for example, and if you look at the top of it, you will have 0, you will have 1, you will have 2, you will have 3. It actually increases as you go down on the scaling. So it's really important when you take a reading on something like a burette that you do a proper reading. So for example, if my volume was right here between the 1 and the 2 marking, that actually is 1 point something, not 2 point something, because it does increase as you go down. So it's really important. What you're measuring is the difference between here and here, which is 1 point something, not 2 point something. So very commonly people will read it incorrectly because they're kind of used to reading the other direction. So it is important with a piece of equipment that you understand how to read it and you understand the scale of it. The other really common mistake that people make with something like a burette is, for example, let's just say this whole thing is a 50 milliliter burette. People oftentimes, when they use it, will go to the top and go, cool, it's filled to the top, it's 50. And that's incorrect as well. So these things have a scale on it, and you should always read where it's at on the scale, not like the total volume, even if it's just 0, because you will get the wrong answer. So it's really important, especially when you're using a burette. People make those 2 very common errors, which is, they kind of read it wrong because it's increasing as you go down. And they oftentimes will kind of just go, okay, I'll just start with the total amount and kind of go downward, and you'll get the wrong answer. So with that being said, why don't you take a look at this one and figure out what the proper reading here should be. So take a moment there. For which one? 0.00. Yeah, because if you filled it all the way to the top, it would be right here. And well, it depends on the burette, but it would be something like 0 point whatever it is, 00. Yeah, so it's very common people screw that up. And it's because it comes out the bottom rather than you pour it out the top. Yeah, like a lot of other pieces of glassware. So it is different. Yeah. All right, so take your reading here and see what you get. Okay, so let's take a look. So once again here, we're going to do our normal thing. So big marking there, 28 and 29. So our large marking in this case is going to be 1 milliliter. If we count up our markings between them, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 in this case. So again, if we divide that by 10, each of our small markings here is going to be 0.1 milliliters in this particular case. That would mean that this is, again, a burette, so it's increasing as you're going down. This right here would be 28.1, 28.2, 28.3, 28.4, 28.5, and so forth. Again, it's increasing as it's going down. So you definitely want to make sure you're reading it the correct way in this particular case. And that would mean 28.6 here, 28.7, 28.8, and 28.9. There, 28.8. So to me, the meniscus is, in this ballpark. So we'll go with at least 28.8 is at least the certain numbers here. These are our certain numbers. I know for sure if I take my smallest marking and divide it by 2, that's going to give me a plus or minus 0.05 milliliters, which means when I take this reading, how far should I take it? How many decimal places? Should take it to 2 decimal places, which means now I need to do my estimate here. And again, you could feel like it's halfway there. Maybe it's more than that, so you could go with a 7 if you like, and milliliters, and that would be my uncertain number. And again, we would have, say, something like 28.87 milliliters plus or minus 0.05 milliliters in this particular case. Any questions on that there? This would have how many significant figures? 4. Uncertain number in this case would be the 7. Yeah, would be our uncertain number in this case, the second decimal place. Any questions on that? So really, really important to always look at the equipment, always look at the scaling, and you do have to decide in some cases which way that scaling is running, right? Is it running higher as you go down, higher as you're going up, and make sure you understand that. I would say 9 times out of 10, glassware like graduated cylinders and stuff like that, it just increases as you go up. This is one of the few that increases as you kind of go down the scale. Any questions on that there? All right. So why don't you try this one, another burette here, and see what it would be. Gonna look again, normal sort of procedure. Large markings is 10 milliliter difference. If we count it, that is 1, right there's 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, if we divide that by 10, small markings in this case is actually 1 milliliter. So again, even though this is a burette, it has a different set of markings, so a different scale than the one we were looking at a second ago. Again, if you just want to figure out how far you should take this reading to, if I divide that by 2, plus or minus 0.5 milliliters, which means I should definitely take it to 1 decimal place in this case. So clearly, if we take a look at it, it is hanging, I would say, right on that second marking. And again, since it's increasing as you're going down, that second marking is 22 milliliters. So remember, we got like 21, 22 increasing as we're going down in this particular case. Now, because it's dead on that, should I record only 22 milliliters? Would that be correct? It would be incorrect based on our scale because we know we can go to that first decimal place. So to maintain the proper number of significant figures, we got to go 22.0 milliliters plus or minus 0.5 milliliters in this case, which would give us our 3 significant figures in this particular measurement. And the last 0 there, right, being our uncertain number. Any questions on that one there? So super, super important, right? Taking proper measurements to make sure you get that. Actually, that was on there. Well, nothing moved on this one. All right. Any questions on how to properly take measurements? All right, then, since we've kind of talked about taking proper measurements, the idea here is those represent significant figures. Significant figures are really important. As I mentioned before, in terms of calculations and so forth, again, your calculation really is only as good as your worst significant figures, our measurement. So let's talk about the actual rules of counting significant figures. The first rule is pretty simple. Any number that is a non-zero is always going to be significant. So we always start counting left to right, and we start counting significant figures once we hit the very first non-zero. So once we hit that very first non-zero, we start counting. So in this case, starting here, that is a non-zero. Everybody else is a non-zero. So that is 4 significant figures on this particular number. Now, zeros are the ones that usually will give people a hard time. And there's 3 types of zeros that we come across. There is what is sometimes referred to as leading zeros. Leading zeros are not significant. So you could have 1,000 zeros before you hit the very first non-zero number, and none of them are significant. So if we take a look, we would go left to right here. These are all zeros that come before the first non-zero number, which is the 4. So none of those zeros are going to be significant. We would start counting at the 4, which would be significant, and also the 9 would be significant as well. And that would give this number here 2 significant figures, the 4 and the 9, with the last 9 there being the uncertain number or the estimated digit in this case. The next type of zero is what's sometimes referred to as trap zeros, captive zeros. These are zeros that come between 2 non-zero numbers, and those are going to be significant. So here, if we start counting left to right, we have a 5. Now we have 2 zeros that are trapped between another non-zero number, and that makes them all significant here, and that would have 4 significant figures. Again, our last 4 there are going to be our estimated digit in this particular case. Now, probably the zero that gives people the worst problem is what is referred to as the trailing zero. The trailing zero may be significant. It may not be significant. What accounts for whether or not it is a significant zero at the end is there a decimal point anywhere in the number? So the decimal point doesn't have to be right next to the zero. You just need a decimal point actually written in the number to make any zero that comes at the end significant. If you do not have a decimal point written, then it is not a significant zero. So if you have 600 written like this would have how many significant figures? It would have only 1, as there is no decimal point. We don't assume it's there because it's not written, and this would have 1 significant figure. If I wrote 600 like this, it would now have 3 significant figures, as we have a decimal point. So those zeros are going to be significant, and it would be 3 significant figures. Now, in my 600 written like this and my 600 written like so, for the first 600, which one would be the estimated digit? It would be the 6, yeah? So the only significant figure is also the estimated digit. So that is a crappy, if that was a measurement, a pretty crappy measurement, because you're basically saying, I think it's like 600, could be like 700, could be like 500. That's a lot of like could be, right? An error in that sort of region. The uncertain digit in the last 600 would be, yeah, it'd be the last 0 here. That's a much better if this was a measurement, right? Because you're saying, I think it's 600, could be 599, could be 601. That's a lot smaller range of uncertainty and error, right, in that measurement. So significant figures plays a big role in error, how good something is, how good overall your calculation is going to be. Also why, like we were talking about earlier, we don't want to just loft off some numbers because you're making your measurement probably in a lot of cases a lot worse than it should be, and that's going to have consequences of that. So if I had a number like this, 0.0010023220000 centimeters, I'm not sure how I measured that. But let's just say it was, how many significant figures would it be? I have no idea, just obviously writing numbers. So let's go through it together here. We'll start with, we'll start here. Are any of those significant? They are not significant. So sometimes people feel like they should be because they're like, hey, those zeros are after the decimal point, right? Problem is, have I hit a non-zero yet? I have not. So I really haven't started counting my significant figures yet until I get to right there. Now I'm going to start counting my significant figures, as that is the first non-zero number I came across left to right. That means that's significant. Are these zeros significant? They are, because they're trapped, so that makes them significant. Obviously significant, significant, significant. How about our zeros at the end? Are they significant? The answer is they are significant, because way over here there is a decimal point. So it does not need to be near the zeros, just needs to be in the number somewhere. And that would give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a lot of significant figures. 10 significant figures in this case. Any questions on that? I think that had all the zeros in it, I think, yeah. We also talked about earlier when we were talking about scientific notation, again, if you have a number that's written in scientific notation, it is anything before the times 10 part is significant. Any questions on that there? Now, when we talk about numbers, there's really two types of numbers that we talk about, really measured type numbers and some numbers that are considered exact numbers. And anything that comes from a measurement obviously is a measured value. It will have a specific number of significant figures associated with it. So anything sort of really based off of a measurement will have a definite number of significant figures. Exact numbers, on the other hand, can have an unlimited number of significant figures. They are basically derived two ways. The most common way in chemistry is they're derived from definitions or equalities, like 1 inch is exactly 2.54 centimeters. Again, you should know that. And again, that is an equality. That is something that is exact. In 1 pound, there's 453.6 grams. That's also an exact sort of calculation. 12 inches is 1 foot, right? So that is also, you should know that one as well. These are all definitions, and they're considered exact numbers. The other way that we could get an exact number is, frankly, if I had these two erasers here, I'm not going to do any type of real big measurement to figure out how many I have. I'm simply just going to count them, right? I got 2 erasers, and that's it, right? Classic textbook example, you got apples in a barrel, or a basket, you're just going to count how many apples you have. So anything that is counted, anything that's considered an exact definition would fall under exact numbers. And what that means is they have an unlimited number of significant figures. The good news about exact numbers is when you're doing calculations, you could just forget about them. You don't have to worry about significant figures they have or anything like that. So if you're doing any type of conversion that is sort of a English to English conversion or metric to metric conversion, those are all considered exact numbers, as we'll talk about. If you do cross over from English to metric, you usually do have to look at the significant figures, and that's not considered usually an exact number, except for this one, which is kind of a common one. All right, so obviously if we take a look at these here, top one, again, we're not going to start counting until we hit the 3, and that's going to be 3 significant figures here. Here, this is scientific notation. Remember, we're not going to take it out of scientific notation to figure out significant figures. The way it's written is how many it has. So that has 4 significant figures. This has 3. All of those are significant. Once again, 1 is significant. The 0 here is not, as there is no decimal point written in the number. So it would have 1 significant figure. And lastly here are 9 significant. We're not going to count these. This is our first non-zero number. Significant 0 because it's trapped. This 0 at the end is significant because there is a decimal point. So the 9020 here, part of it, is our 4 significant figures in this case. Any questions on that there? All right, let's get that. Let's talk a little bit about rounding, which is really important as well, and the importance of not doing any crazy rounding. Normal rounding rules apply. Again, if the digit where after where you want to round to is 4 or less, we typically will drop the rest of the numbers. If it's 5 or more, we typically will increase it. You definitely don't want to do any type of weirdness. So let's say I have 13,333 and I want two significant figures in my answer. What is a proper number here? Is 13 proper? Is 13,000 proper? Is there a difference between those two numbers? Significant figures. This has two significant figures, which is good. This also has two significant figures, right? Which is also good. So you may be thinking to yourself, maybe there isn't really a difference. The answer is there's definitely a difference, right? So let's just say again, I owed you money. Not a good day for me at darts or stuff, but maybe it was okay. I owe you $13,333. And I go, cool, I'm just going to give you two significant figures. Here's 13 bucks. Probably not going to make it out the door. I don't know. Maybe your knives are nice. We'll see. That is definitely a big difference in the meaning of the numbers, right? There's a big difference between $13,000 and $13, right? So although this does have two significant figures, you change the meaning of the number, which you never ever want to do, obviously, when you're doing rounding. 13,000 still has two significant figures, and it also still has pretty much the same meaning, right? 13,000, 13,333. Maybe you give me a teacher discount of $333, for being nice. But it doesn't really change the meaning. And you want to be really careful of that. Sometimes people, especially in this class and so forth, they're so focused, which you should be, on giving the answers to the proper number of significant figures that they do this kind of extreme rounding and you change the meaning of the number. You clearly don't want to do that. You also, by the way, could have done a 1.3 times 10 to the 1, 2, 3, 4, right? That also would have two significant figures, and that's perfectly fine, right? Written in scientific notation, and it maintains the meaning of the number. So you definitely don't want to round extremely, and you want to make sure you keep the meaning of that number. Again, sometimes the only way to get that proper number of significant figures is to write your answer in scientific notation. So again, because you could kind of control the number of significant figures, you want to kind of keep that in mind. Any questions on that? Speaking of rounding, when you're doing calculations, especially if you're doing multiple calculations where maybe you're going to do a calculation, get a number, and then take that number, do another calculation with it, get another number, and so forth and so forth. If you're doing multiple sort of steps in a calculation and you find yourself to get an answer, you definitely don't want to do a lot of rounding until the very end. So typically you want to wait to the very end of the calculation to do the rounding, because each time you kind of round that number and then you take it and do another calculation and round it again, you're actually going to be moving yourself further and further away from the right answer. So you want to kind of avoid a lot of rounding until the end. You want to keep what sometimes people refer to as guard digits, a few extra digits along the way, and that's usually sufficient, especially when you're doing calculations, that you won't have any rounding type error on your answer. Any questions on that there? Again, I would not round if you're doing multiple calculations to the very end, and then you should clean it up to the proper number of digits, which, since we're out of time, we'll talk about next time as to how to get the proper number of digits. But you definitely don't want to round along the way. So let's just say I got an answer that was 1, 2, 3, 6, 5, or something like that, and you know, and I wanted to kind of take this number and do the next one, but strictly speaking, like it's supposed to have one significant figure at the end of this or something. You wouldn't want to just round it at this point, down to the one significant figure. You would want to wait and kind of do it at the very end. And that would definitely avoid any type of rounding errors that you have. Other questions? All right, we're going to lay it up there for today.